Hello, everybody, and welcome to the June Public Inventors Gathering. There is actually nobody here except myself, which is fine because I have to apologize. This is going to be one of our least interesting talks. Just this Saturday, we had the Public Invention Con 2026, and so my staff and I are exhausted from that. It was a big success. We had 68 members of the public there, not counting our speakers, presenters, sponsors, and staff, where we presented a wide variety of things during an all-day event from 9 to 4. And it was a very good time, very, very successful. Today, however, I'm going to talk to you about a slightly different matter. This is going to be a relatively short talk. So hopefully you can see this. I'm going to talk to you today about the idea of a rapid gadgeteering interface. It's a short talk on a relatively simple idea. At the conference, I was able to talk about the Unix Way. And this is something that's been written about in books. Unix was sort of created in the very late 60s and early 70s. And uh, this approach applies to software, but can also apply to hardware. And that's exactly what I'm trying to do here. So the Unix way is to write programs that do one thing and do it well, to write programs that work together, and to write programs that handle text streams because that is a universal interface. Now, if you're not a computer programmer, that's going to be a little hard to understand. But in some ways, the DOS system from Windows and the shell within a Mac system uses this. The famous operating system Linux is a sort of a copy of Unix in a way. It's a variant of Unix. So how do we apply these ideas to hardware, and in particular open source hardware? Well, it's not obvious, but we can build hardware modules that do one thing. We can build hardware modules to be as composable as possible. Now, that's not quite the same as it is in software, but we can do it. And to build hardware to connect with standard electronic and physical interfaces to be as universal as possible. Now, there isn't one universal way of doing things. Some systems really only need 3.3 volts. Some systems are 5 volts. Some systems need 12 volts. There's no way to have a standard that encompasses everything, but we can try to do it. So if we think about Unix way maxing, we would make machines that are physically composable of modules. But all machines are physically composable in a sense. The question is really the time it takes to compose or decompose the modules. For example, a breadboard allows electronic circuits to be quickly composed, but is very fragile. Concrete is very durable, but takes a long time to compose and decompose. So for electronic gadgets, what is a good compromise? Well, we have created a repo where we're, as always, that's what we do at Public Invention. Everything we do is open source, where we're starting from an example of a real device. And I'm going to stop sharing my screen now to have the cameras focus on me. This is the Krake device. This is a general purpose alarm device. You can think of it as a programmable smoke alarm where what it warns you about is something other than just smoke in the environment. It has a loud speaker which can pronounce pre-recorded human voice messages like a hose is disconnected or some other kind of message. It has fairly bright lights that can be easily be seen from across the room that flash when it's on. And it has an LCD screen with 80 characters to tell you what the alarm is. Now, this was demoed at Public Invention Con. It's one of our more mature products. And we would be very happy if someone wanted to take this completely open source design and manufacture it. But no one has expressed interest in doing that. Nonetheless, this is sort of a minimum viable product, though no doubt in the future there will be other examples. And it fits nicely in one case, but it does have separate functions. And if we had been using the Unix way completely, we would have separated those functions into composable physical modules. And I propose that as an experiment, we should try to do just that. And I'd like you to come along with me in this journey as I attempt to show how that might be done, although it has not yet been done. So this is sort of a schematic of how the Krake could be put together with physical modules. And the idea is we layer them together. Okay, this is not really like Lego bricks in terms of its what we're doing, but you may want to think about that. So the idea here is we have a rotary encoder part here, and you could make that a separate module. You could make the LCD a separate module, which is stacked on top of it. You could have the flashers, instead of making them vertical like this, they could be made horizontal into a very thin module. And then the relatively large speaker enclosure would be on top of that. And then, for example, you can add a battery. This doesn't actually have a battery. It has to be powered with a 12-volt power supply right now. But you could add a battery. And then on the end, you could make an end plate that would fit on the end and be a nice cap, maybe with rounded corners and so forth. So if we think about this, how could we make this so that it could be fit together and be sturdy in a way? And what I would like to try to do is to use dovetail joints. So if we think of the speaker enclosure as the topmost thing, imagine that I could just slide it off. And then if I turned it like this, there would be an opening where wires could be connected to the part that's inside here. Those wires would be connected, and then I would just slide the dovetail joint back in place. We would then use, hello, welcome. I'm right in the middle of my talk because nobody was here. So I'm just going to keep going, but you're welcome to ask questions after this. I would slide the part in place and then use threaded rods through the end to add a little bit of compression and to lock each of the components in place. Okay, now we're specifying a particular width, 50 millimeters, and a particular breadth of 140 millimeters. The depth, of course, is variable depending on the number of modules that you use. Now, how do we, in fact, realize this? Well, we at Public Invention mostly use OpenSCAD for CAD designs which are not, for example, sheet metal. So we use FreeCAD for certain sheet metal designs and other kinds of things, but we mostly use OpenSCAD for things which are designed to be 3D printed. So I've created just the simplest possible beginning of an OpenSCAD file that implements the dovetail component. And if you can see here, each component has a male part of the dovetail and the female part of the dovetail. Now, this project is not yet finished. We're looking for volunteers, but the idea is, although each module would require a tiny amount of OpenSCAD programming, for example, to make the ports for the LCD screen or the speaker enclosure, you would have to do a certain amount of programming, or you could call it configuration or CAD design within OpenSCAD, but the ends would be completely standardized and you wouldn't have to worry about it. Then you would just 3D print the modules. And if, for example, someone wanted to add a new feature to this component, they could do so by creating a battery module. It would just dovetail in, the threaded rods would be bolted in place, and you'd have a sturdy and secure gadget, which is why we call this gadgeteering, with an additional module added. So now a person might ask, why would you do this if it's obviously making the complete system non-optimal. It would obviously be bigger than it needs to be, heavier than it needs to be, in a sense, less sturdy than it needs to be if it's printed in one piece. And the answer is rapid prototyping is so incredibly valuable to test out ideas that it's worth it, even though the finished product would not be that good. Now, of course, if you put the modules together and you're like, wow, this is really useful, people really want this, then of course you could design a single enclosure, which would allow you to compress the space, use it more efficiently, possibly even be more attractive, a little better, and cheaper to make in aggregate than making the individual modules. But as the famous Donald Knuth always said, premature optimization is the root of all evil. So you don't want to do premature optimization in hardware design any more than you want to do it in software design, which is what he was referring to. So I can summarize the principles that we have here. We want to use dovetail joints with pins to allow solid construction. We want to have end caps that allow a complete enclosure. We're going to use electrical specifications, which can't really be complete for any module, but can work for a selected set of modules. And then the Lego bricks, which are not really Legos and they're not really bricks, are infinitely, well, no, I'm sorry. Legos are infinitely composable, but they're of limited functionality. RGI modules, rapid gadgeteering interface modules, have limited composability. Some things doesn't make any sense to put them together, but they have good and complex functionality compared to a Lego brick. So the obvious modules that I would like to make are a lithium-ion battery, a speaker enclosure, which we already have, a rotary enclosure with a display. We already have that. That's often used for example, a 3D printer controller, a top cap and a bottom cap. Less obvious modules would be sensing light, producing light, flashers, radio communications, power plugs, environmental sensors, actuators such as a rotary tool, and a motor controller. So we are currently seeking artists, sculptors, and CAD designers who could work on this project to try to see if we could create a little subculture of people who fill out this ecosystem with a large number of composable modules using the format that I've initiated. Of course, later on, there might be other formats. For example, we could make the whole thing much smaller, and then you'd kind of have small gadgets and large gadgets. So if you are interested in this project, please email me at read.robert@gmail.com or read.robert@pubinv.org, which is the email address of Public Invention, our nonprofit 501c3. And we can talk about adding you to the project and trying to see if we can make something.